Hello everyone, my name is Tony Kim, and I'm going to present Pickle and Custom Binary Serializer today. So to briefly introduce myself, I just finished my undergrad last year, but I have interned or worked as full-time in various companies. Most recently from AI Tricks, I worked as a software engineer. And now from next month, I'll be pursuing a master's degree in data science at University of Washington. So before applying for this talk, I didn't know much about Pickle library, but I just knew how to use dump and load. However, I wanted to delve deeper into how Pickle is implemented and understand how it works internally. So the objective of this talk is to understand the general idea how Pickle works internally and know when is the best to use Pickle, when to use other serialization methods, if that's necessary. And towards the end of this talk, I will introduce an episode where I made my own simple custom serializer, which is very simple. Before we dive in, for those of you who's not familiar with these concepts, I want to briefly introduce Pickle and serialization. So a serialization is converting a data structure or an object into a stream of bytes. And deserialization is vice versa, where you convert the stream of bytes into a Python object or some kind of data structure. And these are some functions provided by the standard library in Python that lets you do this very conveniently. And that serialization and deserialization module in Python library is called Pickle. So now, is Pickle the only serialization method? Of course, no. There are many different serialization methods. For example, many of you have seen JSON on the right and protobuf on the bottom, and or XMLs, and of course there are many others like message pack and so on. So what is special about Pickle? In my opinion, I think the best part about Pickle is that it works with Python seamlessly for almost all Python objects. While JSON is best for its simplicity, readability, and cross-platformness, protobuf is best for its performance, especially for network communication. Message pack is an alternative for JSON when you want faster or smaller serialization than JSON. So now this is actually all you need to know about these 4 APIs in Pickle library. Although many of you probably already know these functions, but I just want to reiterate these APIs so that for those of you who are not familiar can get used to it. So this is the dump function where it writes a Python object to a file. And it returns nothing. It just returns none. While this pickle.dump s with the special s returns a stream of bytes instead of writing to a file. And this pickle.load reads a file and converts to Python object. And pickle.loads converts a bytes object and then returns a Python object. So in most scenarios, when you try to just dump the current state of the Python object to a file system, you will only use these functions. In most likely case, without touching the default parameters, we use it like the following. So this is a one-slide layout of Pickle Protocols. So there are currently five different Pickle protocols as of Python 3.7, but there will be a new one coming in Python 3.8. So starting from protocol 0, it's a human readable original protocol, and it was called text mode. And the protocol 1 is called binary mode, and it's an old binary format. And the protocol 2 is it provides more efficient pickling for instances of classes. And just to let you know, Python 2.3 was introduced in 2003. So So those protocols 0, 1, and 2 are very old protocols. In protocol 3 was introduced in Python 3.0. So it actually supports bytes objects and so on and so on. So in protocol 4, it adds support for large objects and a new framing method. And in protocol 5, it'll add support for out-of-band data. So for now on, I'm going to just build upon Opcodes to actually give you some examples and how it works internally with after a few slides. So these are some key facts that you might need to know about Pickle protocols. So the first one is that Pickle protocol Opcodes never changes, but the new ones are only introduced. So this makes sure that old pickles continue to be readable forever. And if the older unpickler tries to read a pickle generated by the newer protocol, it'll either work well if the newer protocol does not use like higher protocol opcodes, or it'll explicitly give you an error by raising a pickle error exception. So I think this is a very good design, and that is very Pythonic because as some of you already know, the design of Python says errors should not pass silently. So I think this is a very good design that follows the Python philosophy. So now here are some opcode examples. There's int, long, and binary int, and many, and so on. But now I want to emphasize the difference between the left opcode name and the opcode itself. So opcode name is a symbolic name, so that we can refer to it as with more intuitive name. While the opcode itself is an actual byte, 8-bit token that is being written to the pickled byte stream. So now some of you might not be familiar with this notation on the left. So there's \x8a in long 1 and \x88 or \89. So this is actually a special escape sequence in Python string, meaning it's a character with hexadecimal value next to it. So each of them is actually length 1 string. But why are they represented that way? This is because they are not printable ASCII range, not in the printable ASCII range. As you can see on the right, ASCII is actually 7-bit, and the higher numbers are not in printable ASCII range, so they are represented as a hexadecimal representation. So the most important thing about protocol 0 is that it's human readable. It always consists of printable 7-bit ASCII characters plus a new line character. And I'm going to build up the protocols as we introduce some of the common opcodes. Not all of them because there's too many, but some are very redundant, so I think you will get the idea. So we're going to start with 3, integer 3, with protocol 0. When we dump int 3, we get L3L new line and a dot. So if I put that onto a table, as you can see, there's 3 that we dumped with pickle module. And here you can see the opcode L is placed before and after 3. The new line here is to mark the end, but if you were to print that bytes back in Python 2, it would make that string a bit more readable because there's a new line. Remember that protocol 0 is a human readable format. And this last opcode, period, is called a stop opcode. And every pickle ends with this opcode. Now let's try a larger number. As you can see, the pickle byte stream contains the actual string numbers in decimal, not binary. So as you can imagine, if we have even larger numbers, then it'll take quadratic time in the number of digits when we are unpickling. So that was int, or I mean long. So now for float, it doesn't have to end with f, but it only puts float opcode f before the actual string. There's no after one. And if you have noticed, we have two periods at the very end as a stop opcode and also in the middle of the float. Even though this happens, the unpickler is smart enough to parse this correctly. Specifically, the semantics of f opcode let the unpickler to read until the new line character. Although I can explain the details of other opcodes like string, I want to skip it because it feels somewhat redundant, while we want to introduce more collection types like tuple, list, or a dictionary. Let's unpickle a tuple of 0, 1, and 2. So now you are familiar with these red boxes. They are integers that are parsed to 0, 1, and 2 respectively. So starting from the beginning, when unpickler parses this stream, it first encounters this open parentheses opcode. This is an opcode called mark, and which marks the location on the unpickler's stack. So stack is on the right, where the mark is at the bottom. And as we parse these numbers, these are actually appended to the stack when it gets fully read. And so this is 0 and 1 and 2. So now when we encounter T, which stands for tuple opcode, we look at the stack and make all elements until the mark as a single tuple. So before we had 2, 1, 0, and mark. So if there are more things at the bottom, it wouldn't go further, but it only makes tuple until the mark sign. And this P is a put opcode, but this does not do anything right now in this example, except that it writes on top of the stack value, which is 0, 1, 2 tuple, to a memo region. And it is quite meaningless for right now, but I will show you that when this is meaningful in the next few slides. So I'm going to discuss list. So have you ever seen this recursive list object? This was very interesting for me because I haven't seen this before, but and it is even more interesting because the Python print is smart enough to detect that it's a recursive data structure and shortens the redundant part. So let's pickle this weird object. Here, starting from the beginning, mark opcode here marks the current stack location. So on the right, there's a mark sign. And the list opcode actually makes a list with the stacks object until the mark sign. So, but in our case, we don't have any stack objects, right? So until only just the mark sign, right? So so we are creating an empty list, and we will call this list as list 1. Now, put opcode writes the object on the stack and put it on the memo. Since in Python, pretty much everything is an object, so think about this list 1 as more of a reference to the lists. Now, 0 is on the stack after L0, L new line. And then when we encounter A, which is an append opcode, we consume the top of the stack and put it onto the list, which is the next item on the stack. And now we add 1 to the stack. Again, we append it to the list. And now we see a new opcode called get. Get is more like a lookup opcode for looking up objects in the memo. In this case, we look up index 0 from the memo and append to the stack. Now, as we do the final append, list 1 at the top of the stack will be a new element for the list, which is the next stack item. So as a final, there's list 0, 1, and list 1. And list 1 is a reference to the list itself. So that's how this recursive object can be pickled even through the protocol 0. So now I'm going to build a little bit more on protocol 1. So you've seen before that protocol 0 uses arbitrary length of numbers for long objects or something like that. So in protocol 1, it's a binary mode, so it encodes numbers with a fixed digit binary format. So in this case, when I dump 2 to the 8, which is 256, then this binary int 2 always consumes 2 more bytes to the right and make an integer number. So we know when this will end by the definition of binary int 2. So in this case, it's a little endian. And now protocol 2 is introduced to pickle new style classes. And there are some new opcodes introduced for fixed size tuples like tuple 1, tuple 2, and tuple 3. And also a new Boolean type. And when we dump an instance of a class, we get the following. So that's a long sequence. So, well, should I fill this table manually again? So there must be a better way, right? So there's a Python module called Pickletools. It is actually installed already in all your machines because this is in Python standard library. You can use directly from a command line to investigate a pickle file, just like this one. Or you can use it in the interpreter with a function called dis. It probably stands for disassemble. So it's disassembling a pickle byte stream. So let's use that for my previous example. As you can see from protocol 2, it always starts with proto opcode, which specify which protocol it is using. So from now on, from protocol 2 to all the way to like 5, it always starts with proto opcode, and it says which protocol it is using. And the new object opcode here is the one that creates a new object instance. So now we are on protocol 3. So there's not much in protocol 3 except that we can now serialize bytes objects because bytes objects are introduced in probably introduced in Python 3. And yeah. So as you can see here, I serialized bytes of hello, which probably translates to ASCII representation of bytes. This is stored with the new opcode called short binary bytes. So in protocol 4, we have new opcodes for empty set, frozen set, and binary Unicode, and so on. And last but not least, a frame opcode is introduced. So in this example, I dumped a string containing Korean characters that say PyCon using protocol 4. Since if you imagine if there's many small read calls on a file-like object, then it'll have a very, very bad performance, right? So what this protocol added is a frame opcode to let unpickler know how much bytes we can read further. So in this case, the frame is 13. So we can, after that 13, we can read further by 13 bytes. So in that way, we can call less read calls to our file system. So that would optimize the number of calls to read. And there's a new protocol number 5 coming in Python 3.8. So this is about out-of-band data where you can send metadata and reduce unnecessary memory copies. If I understood Protocol 5 correctly, we can send metadata to the out-of-band data. That's different from the main in-band data. And then we can send the memory view of a certain contiguous memory so that we can we don't have to call memory copy or something like that. So if you're more curious, please refer to Python Enhancement Proposal 574. And these are some benchmarks that I found in NumPy community. So blue one is Protocol 4. This is written very small, so I'm going to explain. So blue one is Protocol 4. Orange and green are Protocol 5. And orange one is without using out-of-band buffer. And green is with using out-of-band buffer. And left side is the memory, peak memory usage. And the right side is the time consumption. So from now on, I'm going to briefly introduce how I made my custom binary serializer. So this happened when I was implementing a paper from 2016. And this paper was about compressing neural networks. For example, compressing AlexNet from 233 megabyte to 8.9 megabyte without loss of accuracy. But the official repository did not contain Huffman coding and some other details. So I implemented the paper by making a custom binary serializer at the end of model compression. So now, since we want to make an object to stream of bytes, at the very end, we need byte array to write to a file. In my case, my object was a quantized and sparse NumPy array with a sparse format, meaning that many of the matrix values are 0, so we get rid of those 0 bytes. And I use Huffman coding to serialize this into byte array object. And to make things more simple, I converted everything to string of zeros and ones. And then, since I have string of zeros and ones, I used the following code to convert a byte array object. So for every 8 bits, and of course I made sure the string size is multiple of 8 beforehand. And I converted to int format by giving string of size 8 and giving 2 to let the int constructor know that it's binary. And since my implementation converts everything to string first and converts to bytes, it's quite inefficient. So what I would recommend is to use struct module. If you have some arbitrary primitive Python object, then you want to see, and you can use struct module in Python library. So what struct module does is it performs conversion between Python values and C structs. And so when you call struct.pack, it makes Python object to a bytes object. And when you call struct unpack on bytes object, then it converts back to Python object. And as you can see from the left, you can customize and control endianness, little endian or big endian. And I would recommend building custom serializer with this if you want to just testing things out as a proof of concept. However, if you're very serious and you are building something that needs high performance with larger scale, I would recommend other serialization methods like protobuf. And also, I prepared some miscellaneous frequently asked questions. So one is the difference between cPickle and Pickle. So there's underbar Pickle, which is a Pickle module implemented in C language, which is faster than Python implementation. And that underbar Pickle module was known as cPickle in Python 2. But in Python 2, cPickle and Pickle modules were separate, so the users had to pick one manually. However, everyone wants to use the faster one if that's available, right? So in Python 3, Pickle module imports and uses _pickle if available, and otherwise it uses the Python implementation. In conclusion, if you use Python 3, you don't need to worry about anything. So what can be pickled and unpickled? According to the official Pickle library documentation, these are pickleable objects. As you can see on the first thing on the right, functions and classes and other things should be defined at the top of the module is pickleable, which means that lambda cannot be pickled. And I'm going to show you some example in a bit that the function content is not pickled. So instead of telling you the semantic behavior, I would just like to show you simple code examples because sometimes it's better to understand by looking at the code examples. So here I defined hello, which prints Python Korea is great, and I dump that function object into a file called function.pickle. And after closing this interpreter and then using another interpreter, the new one, then I cannot, so the definition of hello is actually erased. And as you can see, even though I unpickled the function.pickle, the Python interpreter cannot find the hello function. So when you're unpickling, that function must be defined beforehand. So let's define that hello function that we missed. However, I changed the content a bit. Instead of printing PyCon is great, now I define the function to print something else. And when I load the function.pickle from the previous example, even though I call that the same function, since the function contents is totally erased, and it's not pickled, so it uses the current function information. So to conclude, function content is not pickled, so only the function name is pickled, along with the name of the module. In this case, it's under main. So functions are pickled by name reference, not by value. This means that you cannot pickle lambda functions. And similarly, classes, methods, and decorators, which is also a function, are pickled by reference meaning a name, not by the value or the content. For summary, pickle is probably most useful when you want to quickly store Python objects and restore later. And JSON is more readable and simple and cross-platform, while Protobuf is good for performance, especially for network communication. And MessagePack is an alternative for JSON when you want more faster and smaller serialization. And to note, only the function's name is pickled along with the name of the module the function is defined in, and the function content is not pickled at all. And when you're building a custom serializer, I would strongly recommend looking at struct module because that packs Python object into C struct in byte arrays. And I really strongly recommend reading these references if you are very interested. Here's a capture from pickle.py. It has all the Opcodes and Opcode names, and it has very lengthy comments, and it's very helpful to understand. And this is these are the talks from AI Tricks company, and since my talk is the last one, I cannot say that you should go to the previous ones, but yeah, thank you.